Is we're going to do a speed variation of the prime mover. We're going to keep on increasing the speed of the prime mover. That will cause the generator to spin faster and faster. The faster the generator spins, the higher voltage it will produce. The higher voltage it produces, the more load will be applied onto the generator, because we're keeping the load as a constant resistance. Let's say the resistance is 10 ohms. As we apply a voltage to it, it will draw current. If we double the voltage, the load on the resistor is going to increase. If we triple the voltage, again the load is going to become high. It's not going to become double, triple, because that's not how it works. Let's start. So first, we'll take the measurement at 250 RPM. So, Abdullah, can you take the RPM meter and then start by measuring the speed on the generator? So we'll ramp up the motor to go to 250 RPM.
Okay.
When we reach it,
Increasing the speed?
yes, when we reach, let me know. When I'm close, let me know as well. Okay,
150.
200.
150,
180,
181,
189, 208,
Okay, so first reading take it
225,
225 now. 225.
Now,
203,
okay, fine. First reading 200 RPM, take it down. How much power are we generating at 200 RPM? Okay, first we need to measure consumption.
49.8.
Wait. First we'll measure consumption. So, armature current of the motor, armature voltage of the motor, can you take it down? Armature current of the motor is 0.48. Motor armature current 0.48.
48. What next?
30.
What is that?
Field current of generator 1.4. So at this point, the motor is supplying a small amount of power, the generator is generating a small amount of power. So this is first reading. Gentlemen, this is first reading. This is the first reading. Read the previous reading. The field is set. Field voltage and current is set. The field current for generator now is
1.4.
1.4. Because you're spinning the motor slowly, we can take our time. It's not under a high.
Generator current is
This way.
0.
Just till it. So again, this is slow speed for the generator. We're gonna be measuring how much power it is consuming, how much power it is generating.
What about the load? Constant?
Load will be, the resistance will be keeping constant, but the load being applied to the generator is not going to be constant. So armature current, armature voltage is there on the body piece. No, it's not.
Armature
Wait.
0 current.
We have to move it over for the current measurement.
0.01.
It is 0.01. You can take it.
0.01.
It's a very small current.
48.7. Sorry, 48.7 voltage. 48.7.
Next,
Okay.
I can smell it as well. The brushes are burning.
What is there?
From which side can you see? Okay, I
From
see.
the field.
Turn it off. The field is overloaded. Can you turn the kit off? So, let's start the motor. So, Abdullah, can you start taking the RPM measurements? The kit is turned off right now. So, what you have to do is turn the kit on, turn the power on, and then can you turn it on? There is power supply. Press the on button to turn it on. Okay, stop. Now can you slowly rotate the supply? Slowly rotate. Now the motor is starting spin. Rotate. Rotate. Keep on rotating until this goes to 1.4. Rotate. Keep checking on RPM. What's the RPM of the lab?
187, 200, 200,
Okay.
300, 360, 400, 408, 457, 520, 600, 7, 800, 1000, 11, 12, 13, 1376,
Now, can you take this reading down? 1380. First of all, the
Armature current 0.69.
0.7.
Field current of 1.8. Field current.
Bring it up, bring it up. Reduce.
Ready, sir.
Reduce. Okay, bring it back to 4. Bring it back to 4. Make it a maximum. Make it a maximum.
Maximum.
Yeah. Fine.
Nice.
The armature rate is 0.16.
0.7.
Armature 1 second. Current is point.
Wait. This is for the motor field.
Armature current, armature voltage, field current.
This is
Armature current.
This is field. This is armature. Field current is not there. Fine. Okay, fine. Armature current is 0.71. 0.94.
Field current 0.71.
Okay, fine. And that is the
Armature voltage.
Armature voltage. This is field current.
of generator.
Generator. Yeah.
Generator field current 1.7.
What is this?
Filter is output of generator. So, this is how much power is going into the armature of the generator, into the load, which should be 0. This is output of generator. Why is there current for open circuit?
Are you sure the connection? Is it the output from
Can you turn it down? Reduce, 0. Slowly to 0. Okay, the generator is. Why is there current draw though? Because it's open circuit. No need to switch off. Bring it to maximum. Okay, so measurements. Armature voltage, armature current.
armature voltage? 384. Generator. Current is 0.34. Okay.
238.8.
Switch off, switch off. The motor is under too much load.
So when
So why do we do the experiment the way we do? Basically, the kit is made up of the AC machine and then it is coupled to the DC machine, which is then coupled to a friction belt. So basically we have to test the AC machine while the friction belt is connected to the DC machine. So we are in a situation where we have to isolate this DC machine completely and test only the AC machine. To achieve this, we have to first of all characterize the DC motor. The thing is that when we have to characterize the AC machine as a generator, we have to test it in isolation. So let's say the AC machine produces 100 watts of power and the input power to the DC machine was 2000 watts. What is the efficiency? Is the efficiency 100 watts divided by 2000 watts? The answer is no. Why? Because the DC machine also has an efficiency. The DC motor might have an efficiency of 50%. That means that the power formula for calculating the efficiency is 100 into 2000 multiplied by 0.5 instead of 100 divided by 2000. So basically, in short, we have to isolate the AC machine from the DC machine when we have to characterize it. So the first thing we have to do is to characterize the DC machine. To characterize the DC machine, we have to get, first of all, a few baselines. The first baseline is the dead weight of the motor. How much power is wasted by the motor simply spinning. So we can first of all measure that by decoupling the DC machine from the AC machine. So we have a coupler present here. This coupler is connecting our two machines together. So basically what we do is we check how much power it consumes while the AC machine is connected, how much power it consumes while the AC machine is disconnected. So there is sheet number 1, zero load. Sheet number 2, base load. So for zero load, no coupling is present. And base load, coupling is present. So what we do is we connect the machine in a way that only the DC machine runs and then we have complete isolation between the two. So this part is completely disconnected. Now we run the machine to get the zero load characteristics. The zero load characteristics are achieved by ramping up the motor and then measuring it at different voltages. So speed is proportional to the voltage that we apply to it. So speed is proportional speed being proportional to voltage, we will create a data set which is ramping up the speed and then measuring how the motor performs. Basically, we measure the voltage that we have to apply, we measure how much current it draws and what RPM it is running at. We can use data such as this to characterize the motor in two states. One of them is the zero load state, one of them is the base load state. So for the base load state, we have to connect the motor using a coupler. So the base load state has the coupler connected to it. Then the third test that we have to perform is the characterization of the DC machine with the load connected. So basically we have to run the generator experiment. This is a little bit backwards. We cannot do this in a forwards direction. So then we have to run the generator experiment just so we can obtain how much power the motor is consuming while the experiment is running. So as we ramp up the motor, we will get values for our generator as well as for our motor. So while we are making those measurements, we have to keep note of how much the motor is loaded. So then what we do is that we replicate that load. Basically, if the motor was under 100 watts of load, we replicate that without the generator running. So it is a bit twisted, but the thing is that this has to be done once. So if this measurement is already done, you don't have to worry about sheet number 1, sheet number 2, sheet number 3. So again, sheet number 3 is characterization of the DC motor, which is using a fixed load. After this is done, you can test the AC machine as many times as you want. Roughly speaking, the characterization will be valid. So this basically allows us to determine the efficiency of the motor across its different performance levels. So at low speed, at medium speed, at high speed, and so on. So because we have the efficiency throughout the motor's curve, we can eliminate that and allow us to get the generator efficiency in isolation. As I said, to get the generator efficiency, it is the input power by output power, but input power multiplied by efficiency of the motor and then the output power. So sheet number 3 allows us to get the efficiency under load. And then we have to replicate the load based on how much load the generator applies onto the machine. So when this generator is running, you have to see the X amount of load that it applies. Then we have to replicate this X amount of load onto the friction belt. This procedure has to be done once, as I said. So this procedure has already been done, and then we can look at the Excel sheet for the generator. So this is the Excel sheet for the generator and motor characterization. So first we have to run the motor at different voltages. So in this case we have ramped down the motor. So we have started at the highest voltage of 182 and ramped it down and checked how much current it consumes, how much power it is consuming overall based on the field as well as the armature, and then how much load is applied. In this case the load is 0 completely. The friction belt is not at all engaged. The shaft tension is 0 because of that, and we also measure the RPM. The friction exerted is a calculation, shaft torque is a calculation, power is nothing, and the efficiency will be 0 because there is no output power. Again, this first sheet is done with the motor completely isolated from the friction belt, completely isolated from the generator. Then we use the generator as a dead load. We connect the coupler of the generator to the coupler of the motor, effectively having the generator as a dead load. The generator has no electrical connections made to it, so it is completely acting as a dead weight. Then we perform this measurement again, and then finally we have to go to the full load motor experiment. Again, the full load motor experiment is a little bit complicated for the reason being that you have to test the generator first, and then you have to do the motor testing. You have to test the generator and see how much electrical load is applied onto the motor. Based on how much electrical load is applied onto the motor, you replicate that load using the friction belt. So the friction belt has a fixed load applied to it. This fixed load is based on how much power the generator consumes from the motor. Then we have to look at the generator experiment as well. So basically we are applying a force using the motor, which is having the armature input power. Phase will be taken as 0 and the power factor will be taken as 1, as it is a DC machine. And then we measure the output power from the AC side. We use the motor efficiency, which is calculated from the previous sheets. This is a complicated formula. You can have a look on sheet number 3 if you want to look at the efficiency across the performance range. So based on the efficiency across the performance range, it is calculating the power. As I told you, the output power cannot be used with the input power to calculate the efficiency of the generator. You have to output power by input power, and then you have to multiply the input power by the efficiency of the motor. That is why this is required. And this efficiency of the motor can only be achieved if we isolate the motor from the generator. The generator acts as a dead weight to the motor, so we cannot measure the motor in isolation. So basically, the DC machine has two loads. One load is the dead weight AC motor, one load is a friction belt. Some power is going here, some power is going here. So the output of the DC motor output is equal to dead load plus friction force or friction load. So we have 1 and we have 2. So to isolate number 1, we have to perform the 2 experiments in sheet number 1 and sheet number 2. Otherwise, we are neglecting the fact that there is power being sent to the dead weight, and that dead weight power is not being able to be measured. So coming back to the Excel sheet, we can then use that to determine the prime mover power, basically how much power is being fed from the prime mover into the generator, and then we can take the generator field power, which is power being consumed by the generator on the field, and then we can calculate the efficiency finally using all of that. And the efficiency peaks at 65% when we are drawing a good amount of power from the machine running at a high RPM, and the efficiency bottoms out nearly less than 1% when we are not applying much rotational power to the generator. The reason being that the field is still consuming power always, depending on the input to it, and it is not dependent on the speed of the generator. So, but in the most of it. So that is it for the complicated and convoluted calculations. Hope you understood some of it. But the thing you have to remember is that you only have to perform sheet number 4 experiment if the first 3 sheets are filled out. As long as the first 3 sheets are filled out and then the prime mover efficiency is already filled out, you are good to go when it comes to performing the AC machines experiment. If you want to do it thoroughly, you can do all 4 sheets from scratch. And thank you.